Hey, welcome back. I am connecting to the YouTube stream and we should be up and running in a second. So I'll just check our audio and video. Connecting to the YouTube stream and okay, looks like we are good to go. All right, thanks so much for your work on module 1 so far. I know right now project 1 should be in, homework 1 is done, and I got grades back and added some comments on everybody's work. So I wanted to go through some of the concepts and ideas that we were working on in module 1, and also if you go back and review the work that you had done, maybe this will help kind of cement some of the things that we were working on, this kind of thing. First thing I wanted to talk about was these timer functions and what they're like. Why are we using these? Because there's computational time. There's like what's called the wall clock time, like how much time has elapsed since you ran a function, and then there's just like how much time you think you're waiting for something to happen, which might have. And all of those have different factors involved. Okay, anyway, so jumping into homework 1, I'm going to skip down to where I saw most people using the timer the way it's supposed to be, which was kind of this last function where we were using time it to actually predict how long it would take to do a really long computation. And really, like the things that people were saying is like, oh, it'll take a quarter of a second or maybe like 2 seconds instead of milliseconds. But yeah, running this 100,000th order time, it doesn't actually give us anything back. So let's just restart. All right, so this is also just a tip that I noticed. At the very top, the first thing that's here is this import NumPy, import matplotlib. I like this 538 plot style. You don't have to use it. There are other plot styles, but this one's good. It has like bigger thickness for plots and these kind of things, better text, better readable text. So anyway, so here's a little trick. Restart, run all. It's going to start at the very top and run through every cell that has something there. So now any cell that had work in it, like anything that has code, it goes 1, 2, it skipped this one, there was nothing there, skipped all of these, it ran this one, and then came down and ran 4, 5, and now number 6. Okay, so let's run a time it, exp Taylor, there we go, of 1 and 2, and it'll take a couple of seconds to run it. Then we'll time it and say exp Taylor of 1 and 10. And if we look at what this function is doing here, when we said 2, it skipped over this if statement and went into this else statement. So else, then we say 1 plus 1, so it becomes 2, and then going from 1 to 2, so just 1, it's going to add 1 to the 2 over factorial of 2. And what we end up with is like 2.5 there. Okay, now this one took 484 nanoseconds. This one took 2.47 microseconds. So let's see how much longer 2.47 divided by 0.484, 5.1. So when we said we want 5 times as many calculations, the actual time that it increased was like a factor of 5.1. So if I go from 10 to 100,000, it should be like every every factor of 5 should be kind of 5.1 more. Some people just rounded that to like a factor of 5 is, so 5 times more calculations is 5 times more time. So 100,000 or 10,000 more is going to be 10,000 times this thing. And that's a good way to do it too. So we would say like 10,000 times that 2.47, and let's divide by a millisecond, or sorry, microsecond is 1e6. So according to this, it's like, let's go 1e3, 24.7 milliseconds, something like that. All right, so now let's talk about like what this thing is doing. The time it here is, so one, it's telling me that it ran this function a million times, and 7 runs, a million loops each, and then it gives me both an average and a standard deviation on how long the computer took to run that. This is different than like the wall time. Python wall time. And just Stack Overflow. There's a time it dot time, because I saw this one, time access. Where is it? Python get time. So there is a Python time it function, and that one works. What we're using here, this is called a magic command. It's specific to Jupyter. It's a nice way of using like extra functions, but we could also say like import time it, and now we have access to time it module stuff. But anyway, so I saw some people try to like grab what is the current time and then run a function and then say what is the time now. But that one has to do with that one changes based on how long it took to send the command, how long it took to get the command back. This time it function is just looking at how long was the computer actually using resources to run this. And that's really more of an important thing, at least in this case, where we're looking at like one function and deciding in our case right now, it's like how big does n need to be so that exponent Taylor, so our Taylor series actually converges to a reasonable result. So we're doing an optimization here. We can wait longer, like a 10th order, 2.5 microseconds is not that long to wait, and we don't even notice the difference between half a microsecond and 2.5 microseconds. But if we're going to run this 60 billion times, then it starts becoming more important. Like, is this going to be a bottleneck in our code? So that's where time it is really valuable. Just looking at very small snippets of code, and what the only difference here is a 2 and a 10. So very small. So let's take that learning of what we just did and come back up to this problem. It's called problem 2, but really it's problem kind of problem 3 or whatever. I don't know. The numbers get all weird. They're supposed to auto update, but sometimes they don't. So anyway, we're going to use a for loop and create A99, and then we're going to create A99 using NumPy, and we want to time the difference between the two. And so really this is saying, like, use the mean standard deviation, look at the time it difference, and I go back and forth on that. Sometimes I think maybe it's worth it to leave this mean and standard deviation part of that, or just separate it out. So I'll show you just the simplest case. And this is, so A99. So if I just want to use for loops, this is a great like Python specific way of doing things. So I'm going to say I times j. Notice how I put 2 sets of parentheses here, and I'm putting an I and a j inside here. And in most languages, what I would have to do is say for I and then a for j and kind of go through this way, but I'm not going to do that. What I'm going to do is say for I in range 10 and for j in range 10. And this is called a list comprehension, where I'm actually putting the for loop inside of a list. For if I'm trying to make just general kind of lists and not NumPy arrays, I can do all sorts of great and interesting functions this way. And you can probably come up with your own examples that are more interesting than just multiplication tables, but that's what we have. And then let's just troubleshoot to start. Just see if it gives me what I wanted it to. So I have a row full of zeros, a column full of zeros, so that's 0 times 1 through 9. And then I have 1 through 9, 1 through 9, and then 4, 6. So this is the row with all the 2 times 1, 2, 3, 4, 5, all the way through 9. And down here I have like 9 times 1, 2, 3, 4. So I have the full multiplication table in there. And I can look at the mean of A99. I can look at the standard deviation of A99. And these two values are meant to give us that if we created A99 the right way, then this mean and that standard deviation should be the same whether it's an array or it's a list of lists, which is what I made here. Okay, now let's look at like timing it. I'm gonna just take this and run it here. And I'm only looking at that creating A99 because mean and standard deviation, those are going to be the same time, whether it's NumPy is going to immediately put it into an array and then run the calculation. So this took 6.5 microseconds. Again, not a lot of time. It took longer to like type it and send it back and forth than it did to calculate it. Okay, so let's compare that to, so if I have an x times y, let's double check that it's actually what I want. I get the same multiplication table. And I get the same mean. And the same standard deviation. And there's no, let's see, 612935, 612935, 81405. So it's exactly the same, which makes sense because we're using integers. Like we shouldn't have any round off error as we're trying to store these. Now I'm just going to take this, let's put it right below this one so we can look at it directly. This one, I ran it again, still took 6.5 microseconds. This one takes half of a microsecond, or less than, so 400 nanoseconds. This is the number that I'm looking for, that using for loops should take a lot longer than using NumPy arrays. This one is backed up. It has a lot of like speeding parameters that help it speed up, and a lot of functions built in C. This is the numbers really that I'm looking for as I'm trying to like compare a for loop versus a NumPy array calculation. So think about it. The main thing that I saw people really getting tripped up on was like, if I import NumPy as NP and I import matplotlib.pyplot as PLT, if I do all this inside that time it block, then there's no way to tell which one is, well, this one, this one's still faster because I had already loaded it. So it was already like in my cache. But the next time, sometimes, or if I restarted the kernel, it would be a different amount of speed. It's still faster somehow. Normally it's not. Here, let's do a restart. I'm running things like a little out of order because I just didn't want to get an error on it. So let's run it again. Nanoseconds, wow, okay. Normally this takes a lot longer to import functions, but it doesn't have to do, it's probably just like loaded up in my server at this time. But anyway, I'm not trying to time how long it takes to import things. I just want to know, like, if I'm using NumPy, how long does it take to create that A99 array? And if I add that, the mean A99, let's just do that. So we'll run those two. It starts to get murkier because the metaphor that I've heard used is you're trying to weigh the captain by weighing the ship with and without the captain. So if a ship is 3 tons and the captain's 150 pounds, it makes a lot more sense to just put the captain on a scale rather than put the captain and the ship on the scale and then try to see what the difference is. There's still a difference. Like, it's still faster to use NumPy in this case, but it becomes harder to find that. The more and more stuff that you add into that time it function, the harder it gets. Okay, so that's using the timer, and it's a really great tool, and it'll help as you're building bigger functions and kind of like playing around with Python. In general, I'm not too worried about timing things. Like, it's something that I do because I'm interested, but really my first goal when I'm trying to program Python and even like engineering stuff is just get it to work. I don't really care if it's a couple of microseconds faster because I can just let it run overnight. And usually like big abstract tools, they do all sorts of other stuff. But anyway, okay, cool. Now, what I wanted to take a look at was this FizzBuzz example, because I saw a lot of people kind of get into the same idea of just compounding if statements, like an if this, if this, if this. Okay, so what I saw was like for, let's say like n equals 20 for I in range of n if n percent 2, or I guess we start with 3, oh yeah, first people did this. If I could spell. And let's add this. And then what I want to do is print I and str out. Oh. Let's do my magic. So if you hold Control and click in multiple spots, then you have like multiple places that you're typing all at once. All right, and then else print I. Okay, so this is what I saw most people do, and it works. And again, like as engineers, like all we're really trying to do is just get something that works. There's other ways to do it, but what I wanted to do was walk through like why this is working and some of the things that we have to look out for here. Okay, so I have like 0 through 19 all kind of put in there. And actually, let's go all the way to 31 so we can check. This is the last case. So 0 and 30, both of those are factor. They have 3, 2, and 5. They have no remainder there. What's happening here is that each of these if statements is getting checked on every time I have a new I. So first I is 0, and it checks, is this true? It's true, so string out is computational. This one's true, so string out becomes computational plus this. Then this one's true, so string out becomes computational plus mechanics plus rocks. And then this one's kind of tricky. For a string, if a string is empty, then it's false, and if a string has anything in it, then it's true. So so if any of these, here, let's do this. If print empty, so with an empty string, nothing happens. But if I put anything in it, doesn't have to be the word anything, then it's just going to do whatever. So it's a true statement. So if there's a string, then it's true. If there's not, then there's nothing there. And so one thing that sometimes gets people tripped up is like, all right, if I were to change the location, of this else statement. I'm trying to get it. So if I put the else up here, I'm going to start printing out multiple 2s. So, which is kind of weird that I get a 1. 1 makes sense that there should only be a 1 there. But then there's a 2 and a 2 and then a 2 and a mechanics, which shouldn't be happening. It should, this one is true, so it should just be adding mechanics to that string out. And part of it has to do with the fact that it's running these in order, but the other part is that this else statement is only connected to this one if statement. Every time you put that word if, it's creating like a new logical check. And if that check passes or fails, so there's also the case that, let's see, so there should be a case where that is not 3, so 2 and 5, so like 10, yeah. So it prints out 10 and then mechanics rock. So anytime this 3 is not true, then it ends up messing things up. It gives us 2 outputs for that same, and let's see, yeah, 25. So anytime it's a 2 or a 5 multiple, then we end up with this weird case. And it's okay, it works. But I wanted to show one other. Do we want to? Yeah, let's do that. So I don't know if anyone had tried to do this, but there's also this elif statement. So instead of saying if and else, you can say if this, then that. So if we're doing if and elif, really I would need to start off with the most general case of saying like and then down here, so now let's look at what's happening with if and then elif. So if this statement is true, if all 3 of these things are true, then it prints out what I want, that computational mechanics rocks. If this one is true, if it's only divisible by 2, then it'll print out mechanics. And what I find here is that I'm always just looking at mechanics, because with an elif statement, it's skipping over, it's not going to check, is this thing true? So really what I have to do is go from most general to least general, like this. So now I have like the 5 is not really working correctly yet, but that's kind of the general way of doing that. Yeah, so the nice part about using elif, like if and elif, is that once it finds a true statement, it skips over the rest of the checks. So technically it should be a little bit faster to do if and elif. Sometimes it gets harder to debug. Sometimes it just makes more sense to use a whole bunch of if statements. But usually it's better to use like if and elif. And it depends. It depends on what we're doing. And then, was there anything else? It felt like there was a lot of great work and some good things. I guess let's take a look at this Euler integration real quick. So I can just walk through like what an Euler integration is. So let's say dt is 20 years. T general process for this Euler integration, and we're going to keep doing this over and over. Oh, what is this? Help me write. Anyway, is time is always an independent variable, so I'm the one who controls it. So I'm going to start at 1900, go to 2021 with step sizes of dt. A range works great for integers. It doesn't work as well for like if I wanted to take steps of 0.2. It's usually better to use linspace. But anyway, so set time. I'm going 1900, go to 2021. Now I set the population. I'm just initializing the population. So for every point in time, there's going to be a population. One of them I already know, the rest I'm going to solve for. So I know the initial population at the year 1900 is that pop of 0. And now I start at the second time, so in the year 1920, and go to the last value of time, so 2020. This is so inputs for a range, and this also works for indexing, is start, stop, step size. So I'm starting at 1900, going to 2021, but not including that. So it's stopping there, but it's not including that number. And then it's taking steps of dt, which is 20. All right, now I'm going to say p of I is equal to p of I minus 1 plus that k, I guess I should set it, huh? 013, sounds right. And what I'm doing here is I'm taking this exact differential equation and turning it into one step. That if this is my slope, I'm going to take that slope, multiply it by a time step, and that'll be my change in population. So my current population, my next population is my current plus the change in the population, which is the current times that growth rate, times that dt. And let's just plot t and p. Oh, let's do a kernel, restart, run all. So if plot is not defined, just run everything. Usually that'll fix everything. And now I have this growth curve. And so what I like to do to say that it's a numerical solution is show that it's discrete dots. So now if I wanted to change the step size, I can see the dots are closer together, so I integrated more. And if I can do it once, I can do it as many times as I want, right? So let's take all this for dt in 2, 5, let's go 1, 2, 5, 10, 20. And then we'll say label. What did I do wrong there? Ah, I forgot a comma. And node help, a legend. And what I'm showing here is that as I keep decreasing my step size, as I go from 20 to 10 to 5 to 2 to 1, it's changing, but it keeps changing less and less. So what this is called a process of convergence, where I'm converging to one answer that is the analytical answer. And people were kind of talking about this in the homework, so I wanted to show this example that it does converge to the actual analytical solution, and it's not a theoretical. It doesn't depend on what computer we're using. It doesn't depend on anything like that. All it is if we keep decreasing dt, it doesn't have to be 0. It's going to be indistinguishable from the actual analytical, like the e to the kt solution. And it's just, that's how Taylor series works. It converges, and it's order 1 convergence. So if the time steps are 10 times smaller, then it's 10 times less error. If they're 100 times smaller, there's 100 times less error. And there's other methods that we'll take a look at, and then other integration methods, but we'll get back to those in module 3. Cool. Thanks so much. Keep up the great work, and hopefully this example helps with as you're thinking about like the project one, and I'll take a look at that this afternoon and get some grades and comments back to you tomorrow. All right.